And today we're going to talk about something called DiGraphs. Di is short for directed graphs. And this, believe it or not, is a field of study that is still has a lot of unknowns. And there are researchers working with graph theory, taking a look at graphs and everything. And, you know, some of you have seen, I did take a class in, early 90s. And if I have an envelope that looks like this, can I draw that envelope without crossing over a line or lifting up a pencil? You know, can I visit each one of these? And the answer is yes. You know, I'm pretty sure you can. But I had a class called graph theory, and we had all of these vertices, is what we call them. With our binary tree, we've been calling them nodes. But we had all these vertices, and we took a look at how many edges came out of it. Or what we're going to talk about today is directed arcs. But could you make this envelope in a way that you, I just did it, bum, 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 something like that. And you get into a whole theory about, you take a look at each of the vertices and say, well, how many edges come out? And this has 2 edges come out, so we would actually call that an even. This has 1, 2, 3, 4, that's an even. And then you get into the whole theory of, if you have a certain number of edges, you have to have a certain number of odd edges coming out of the vertices, a certain number of vertices, and you have to have so many, you know, like these are all, there's an odd 1, 2, 3, there's an odd 1, 2, 3. So you have to have an even number of nodes or vertices with an odd number of edges coming out of it in order to draw it. So you see some of those things on Facebook or whatever, and they say, can you draw this without lifting your pencil? And there's a whole study of graph theory dealing with these vertices and these edges come out of it. Well, we're going to get into it a little bit today and how we can tie it into our world of computer science. And I have a little drawing here, and I have A, B, C, D, and E. And I have some directed arcs coming out of here, okay? And you can see the direction that each of them goes. Now, one of the things that I usually do is liken this to an airport to give you a sense of what's going on. So imagine each one of these is an airport, and in its simplest version, you know, planes fly from A to B. Planes fly from A to E. So, you know, you might be dealing with a certain airline instead of all airlines, but you can see places you can get to by the directed arcs. Now, again, do I have a head node here, a root node? Well, no, A is written at the top, but that just happened to be by location. So when I start dealing with these directed graphs, one of the things I don't know is where to start. Right now, you're looking at it as a whole. If I said, if I start in A, can I get to D? And you're going, yeah. You take A, Atlanta, you go and you have a layover in Charlotte, and then you can fly to Dallas, kind of deal. And, you know, you start getting to airlines, and you have, oh boy, all the cities with all of these flights and multiple ones during the day. And you add in weights of, you know, what's the cost from here to add it to there? Or, you know, is it easier, is it cheaper to go from A to B or A to C to B? Just all kind of different things. And so I sometimes liken this to what's going on with airports, or, you know, you could have distribution hubs or all these different things. But one of the questions we first ask is, if I start in a certain node or vertice, can I get to another vertice? And right now we have to look at it and say yes or no, depending on the flight pattern. But what we're going to do is take a look at one of 2 ways that we could solve this in our world of computer science. By the way, how many of you got a piece of paper out and tried to draw this while I was talking?
I did it.
You did it?
Mm-hmm.
It's doable.
Yeah.
It's doable. And it also has something to do with where you start. But I think if you go in the middle here and you go down and over and up, and then I don't know. It's doable, but there's
It's only the one horizontal line that I miss without, if we're only supposed to have that shape,
right.
we have to have like another line in order to complete that. But otherwise, it's
Okay,
perfectly possible.
so I just did that much. I went here to here to here, up to here to there, up to there, back down to there, and to there. Ta-ta! I did it with all the
Wait, what?
lines. Didn't you see me just solve that?
No.
Watch. I went here to here to here to here to here to here to there to there. I did it.
Oh, okay.
Yep. There's a big
Numerous puzzles.
there's a big problem called the bridges of Königsberg. If you ever really want to get into it, it's Koenigsburg, and you can take a look at. They talk about people trying to cross all the bridges on this river, and can they start at one spot and so on. But anyhow, let's come back to what we were talking about. And at this point, we're talking about this directed graph, and I want to know, how can I represent this so I can use it in my world of computers? Well, the first way is called an adjacency matrix. And what I'm going to do is create a matrix. It's going to be 5 by 5. And I'm going to go A, B, C, D, E. And hopefully all of you are okay with two-dimensional arrays. And hopefully all of you somewhere along the line have done some matrix operations. And the one we're really concerned about is going to be multiplication. So I'm going to start here. This is my starting node, or my starting vertice. And does A go to A? And you think, well, that's kind of a dumb question. But then remember, over here, I have D going to D. Well, A does not go to A. So I'm going to put a 0 in. A actually goes to B, C, and E. So 1, 1, 0, 1. And I can keep going, filling out this chart. B only goes to C. C goes to B and D. I'm doing this in dark, so hopefully I don't screw it up. D goes to just D, 0, 0, 0, 1, 0. And E doesn't go anywhere. Okay, so let's see. I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I think I got it right. I drew what's called an adjacency matrix. And I can quickly look at this and say, where does C go? C goes to B, and C goes to D. So if in reverse, I gave you a matrix like this, could you draw a picture that might make a little more sense to you? Yeah. So this is all of the ways that I can jump on a plane and get somewhere. So if I say I live in C or B, I want to get on a plane, the only place I can fly to is C. And that's it. Okay. And what I mean by that is of one directed arc, or by one edge. Well, what if I said, if I start at A, can I get to B? The answer is yes. But is that the only way to get to B? Well, the answer is no, because A can go to C, yeah, and then go to B. So this is telling me one trip to get there. What if I'd like to know, are there ways of length 2 to get somewhere? Here's what I'm going to do. I'm going to take this matrix again, 0, 1, 1, 0, 1, and put it beside each other, put it beside itself, 0, 0, 1, 0, 0. I'm just going to keep drawing this out. And believe it or not, if I multiply these two matrices, what I'm going to have is my resulting matrix is the number of ways I can go from, for example, if I look at B and I want to know, can I get to C by 2 ways, with a layover, then that would tell me if that's possible. So are we familiar with multiplying two matrices? Well, some of you know how to do it on the calculator, and if you can, that's absolutely fine. Otherwise, we're going to take row 1, multiply it by column 1, and put the result right here in row 1, column 1. Now, how do we multiply it? we take 0 times 0, the first times the first, plus 0 times 1, plus, excuse me, 1 times 0, 1 times 0, plus 0 times 0, plus 1 times 0. And it looked like that was 5 zeros. So if I add it up, it's 0, which means there are 0 ways for me to leave A, go somewhere else, and come back. So this is, you know, taking 2 flights or 2 trips to get there. If I start at A, is there any way to go somewhere and then get back to A? And the answer would be no. And then I could continue filling this in, going all the way across. So in the world of computers, multiplying matrices isn't really such a big thing. We could go ahead and do that. So if I did row 1 times column 2, I'm doing 0 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 0. When I did row 1 times column 2, it says, hey, there's one way that if I start at A, I go somewhere and then I can come back to B. There's one way to start at A, go somewhere, and come back to B. So this would be all of the ways that I could do that if I continued multiplying this out. Now we have simple graph here. Imagine if I had more edges drawn and put in here. Well, I may end up with multiple numbers, like 4 or 5 different ways to go from one to the other and back and so forth. But the way I would do it is just continue multiplying across. Anybody know how to do it on a graphing calculator?
Yes.
Yes? Okay, good. What's from A to C? How many ways are there if I do a layover?
Just a question again.
Mm-hmm.
So that one right there. So
This one.
so that's only one way, or that's 2 ways?
No, that's one way, which means I'm
Okay.
going to have a layover.
Correct.
So 2
Okay.
flights. Yeah, there's one way that if I want to jump on a plane at A, I can go somewhere and get back to B.
Okay.
Okay. What if I did this third one? I'm doing row 1 and I'm doing column 3. I'm taking 0 times 1 plus 1 times 1 plus 1 times 0, 0 times 0, 0 times. So there's one way for me to leave A, go somewhere, and get back to C. If I leave A, I can go somewhere and get back to C. And like I said, I could continue filling all this in. If you need more help with multiplying matrices, let me know. And that's something that we could work on. But this is an adjacency matrix approach to looking at this and saying, you know, if I'm using these directed arcs, okay, they all have direction. Now, we could even look at these guys without direction, and we'll probably be doing that on Tuesday. How are we making out? So far, so good?
Mm-hmm.
Yeah?
I think so.
Okay. What's D? Tell me what D comes out to be. If I want to go
0 times 0.
0 times 0, yep.
0. Where did it go?
1
0 times
times
0. Oh, sorry. Yes. I lost it. 1 times 0 plus 1 times 1. That's 1. Plus 0 times 0 plus 1 times 0. So that's 1.
Yep. So if I start at A and I want to get to D, it looks like A to C to D. So right now, you know, in our programming world, all we're looking at is it possible? Is it possible? And, you know, we would keep going through filling in this graph, just trying to find out if it's possible or not. What if I said by way of 3? You know, if I wanted to go from A to D by way of 3, you know, I'm looking at A to B, B to C, C to D. That would be 1. A to C to D to D. That would be another way. So again, I would take a 1 tripper and multiply it by 2 tripper to see if I can go, you know, from A to B to C to D to get me there. 2 layovers this time. All right, so far so good. Now, another way of representing these, instead of an adjacency matrix, is an adjacency list representation. And as soon as we start drawing this, it might look kind of familiar, but this is adjacency list. And basically what happens is we're going to say, if I'm at 1, and you might say, oh, look at that, I know what's going on there. If I'm at A, in this case, from A, I can get to B. So if this guy right here is A, I can get to B. Where else can A get to? C and E. So if I wanted to store these, you know, what's the problem with our matrix up here as far as programming is concerned? What's there a lot of? Zeros.
Memory.
Yeah,
Zeros.
yeah, a lot of zeros. A lot of memory is going to be used because you would take the number of
each permutation
vertice,
or whatever.
Right, each vertice, and you'd be squaring it. So that's the amount of memory we'd be using every time. And you know,
plus it's going to take time to do all that multiplication if you wanted to do the thing.
Except we just don't have to do it by hand. That's the good thing. Again, I can represent, does B connect to, let's see, B connects to C, and that's about it. C goes to B and D. So in our world of what we've been learning most of this semester was, can I do it with a static or dynamic way of dealing with it? And to finish this out, D goes to D and E goes to null kind of deal. Now this isn't, you know, you'd have to really get into how I want to work with it, but I'm just drawing the parallel of what we've done pretty much 3/4 of the semester. We've dealt with a topic either by using matrices or by using some kind of dynamic representation where we either did nodes or, what was this called again?
Adjacency list, you mean?
No, this concept, yeah, it was called chaining.
Oh.
Yeah, bad question. I asked the question wrong. Okay, so if I wanted to give you one, I could give you something that looks like, I'm going to give you a matrix.
Is there like a huge difference between like D being able to go to itself versus E like not being able to go to itself, but it's still like a dead end?
Right. What we're looking at right now is baby steps, because I'm thinking that if you had a job and you were working with this, it would be way more complex than that. You know, we were able to get away with a simple drawings because we're still just starting out. But I'm thinking, you know, and again, I used an airport to get us up and started, and I think people understand that. But from my understanding, there's lots of ways that this could be used. And, you know, you get into UPS deliveries, and one of the rules of UPS when they're creating it, you know, if you start looking at addresses and you want to do this thing called shortest path, which is what we're going to do on Tuesday, you start looking at the shortest path. One of the things that UPS is now thrown in is their programmers know not to make it where drivers have to make a left turn, because left turns take longer than right turns. So they've gotten into, how can I eliminate making left turns when I'm, you know, drawing up the route of how I want the UPS driver to go. So it gets kind of bizarre. But like I said, where we are right now, it's just a bunch of baby steps. So I'm going to make up a matrix, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. And my left side's not so good. I should have made it a little bit bigger. And again, in the world of matrices, some of you know that if I'm going to multiply this guy out, it becomes 0A, a B, a C, and so on, you know, because this is our data. But I'd like you now to draw A, B, C, D, and E and go ahead and connect according to the adjacency matrix. Sound good? I'm doing it in a marker so that it's easier for you folks to see. Ideally, I should be using a pencil or a giant whiteboard. But we're going in reverse right now. Let's see. I'm even going to write them across the top. A, B, C, D, E. A, B, C, D, E. A does not go to A, goes to B. C and E. Hey, so far so good. Proud of myself. B goes to A. B goes to D. And B goes to E. C goes to A, B, and itself. Huh. C goes to, uh-oh. Do you like my little jumps that I'm putting in? D goes to A, C, and E. D goes to A, C, and E. He's going to go all the way around there. And finally, E goes to B and D. E goes to D, which is there. Oh boy. E is going to B. So E is going to go here, jump, all the way to B. Now all of a sudden I'm thinking my matrix looks a whole lot nicer than the actual drawing of the picture. Y'all okay with that? Everybody in the club, give me a thumbs up. Daniel gave me a thumbs up. There we go. There we go. That's what I like to see. Okay, so one of the things I talked about is if I want to take a look at this crazy graph, I need to figure out a way, you know, to represent it, which I did, but I also want to figure out a way to, you know, how can I go from A to, where can I get to from A? Where can I get to if I start at C? And I start to ask these questions, and what I need to do is figure out a way to search or you know, traverse through this graph to get places. And it's a little difficult because it doesn't look anything like we've been doing with binary trees and moving left node right and node left right and left right node, our in order, pre-order, and post-order searches. But we're going to take a look at two different ways to traverse or to search through this. Now, this is going to seem kind of weird, but we're going to start with the understanding of this by taking a look at not necessarily a binary tree, but a tree that is close to this, to a binary tree. And, you know, some of you are following along in the book, that's fine. But I'm looking at a tree that looks like this. A goes to B, to C, and to D. B goes to E and to F. And F goes to H. Sorry, I should have prepped this to make it look nicer. And D goes to G. Okay? So I'm starting with A, and I'm just, you know, taking a look at A, not necessarily from here, but imagine if I could take out all of the extra arrows that I don't really need, or, you know, we're going to take a look at this guy. And when we do this searching and traversing, and like I said, we're looking at it from top down right now. Later, we're going to come back and look at it when we have a cluster of nodes or vertices and directed arcs like this. But we're going to talk about two things. The first one is the depth first approach to searching or traversing through here. The second one is going to be the breadth first. And once we get the concepts down by looking at this tree type of shape, then we're going to go back to our mess like we have up here and start to take a look at, can I traverse through and where can I go if I traverse through? Now, a depth first says I'm going to start at A and I'm going to see how far down I can go, like a depth charge. And then once I go as far as I can, I'm going to backtrack and go as far as I can. So I'm going to take a look at the depth first, and we're going to start with A. And, you know, we're used to left to right. So A can go from A to B to E. Okay. And I've hit as far as I can go. So now I'm going to backtrack. I come up to B. Can I depth charge down? Yeah. I can go to F and I can go to H. Backtracking, I'm good, I'm good, I'm good. Now I depth charge down and I hit C. No place to go. I go back up. Are there any other options for A? Yes. I could hit D and I could hit G. So this is a depth first approach. I go down as far as I can, start to come back and keep going down if I can, and then keep backtracking and go down as far as I can. Breadth first looks like this. I'm going to start with A and say, where can A go? Well, A can go to B,
C, and D.
C, and D. So now I'm just going to make a little notation that I took care of A. Now I'm going to go to B. Where can B go?
E and F.
E and F. Good. Now I'm going to go to C. Where can C go?
F.
Nowhere. Nowhere.
F.
C's just, no, I don't have a line from C to F. Yeah.
Yes.
I go to D. Where can I go?
G.
To G. Now I check E. Where can I go? Nowhere that I haven't been already. F. Is there any place I can go? That's H.
H.
Then I go to G. No place to go. And finally H. No place to go. So that was the breadth. I see where all A can go first, and then I say, okay, well, A went to B, where can B go? A went to C, and I continue that process. So we have the depth first, and we have the breadth first. All right, let's kick it up a notch here, Honcho. Let's go with A, B, C, D, and E, B, C, D, and E. I got F and G, and I have an H over here. And finally, I have an I right there. So A goes to B. That's kind of nice. B goes here to F. C goes to B. C and D do a little dance. Do a little dance. Oh, sorry. A to D. A to E, D to H, E to H, oh boy, F to G, G to B. This is out of the book, so it's easier than me trying to make something up on the fly. G goes to C, and F goes to I, and I goes to H. How's that look? Pretty good?
Very nice.
Nice. Okay. Uh-oh, the lid to my bird feeder's crooked. I'm going to have to fix that because we're going to get a ton of rain today from what they say. I don't want all the bird seed to get wet. Yeah. Okay, so we got a pretty graph here. Sorry, I like the squirrel. I don't have squirrels, just birds. And you know, we got going on here. So I want to do a depth first. Okay. Somebody want to get me started with depth first?
Depth first.
Yep.
A, B.
Stop right there. I didn't say which node, did I? So, you know, right away you're thinking, well, it's alphabetical. I have to start at A. And yeah, no, that's not necessarily true anymore. I can do this depth first search starting at any node. So now my question to you is, where would you like to start? Pick A.
I.
Pick
or
A.
G.
Pick A. Pick A.
A.
A. Yeah, you said I. I's interesting. So if I did depth first with I would go from I to where?
H.
H. And from H to where?
Well, it doesn't go anywhere.
Yeah, nowhere, right? And if I did breadth first with I go to H. Yeah, and I go nowhere with the breadth one either. So hopefully on the test, if I give you one of these, I give you something as easy as I.
Yeah,
No, that's not going. That's not going to happen. All right, let's do from A. That seems to be the popular choice. Let's do the depth first and see what you come up with. Do you think you got it, or shall we walk through it as a group the first time, and then I'll give you another one?
Give it a shot.
And give it a shot. Shot to the heart, and you're to blame. You can't. Sorry. As long as we don't need Adelson-Velsky to come into play here. Depth. That means I go as far as I can go. Once again, what's your first choice? Well, you're inclined to go alphabetically, and I bet you said B, but would D be a possible answer to be next? Absolutely.
D or
and or E, right? Or E. I'm guessing you went with B, so let's go A to B,
to F,
to F, to I to
to
H. Okay,
G.
Go ahead. I'm backtracking all the way. I did in fact hear G. G
C.
goes to, where does G go? G goes to B, but B is already used. G goes to C.
D.
C goes to D. D goes to H. I backtrack to the D, right? It doesn't go anywhere else. And I already, so somehow or other, every time I add one, I'm going to have to go back through this list and see if it existed. So when I went from A to B to F, I kind of need to make sure I didn't already hit F. When I went to I, I'm good. When I went to H, I'm good. After H, I went back and checked I. I went back and checked F. I went back and checked B. You know, so when you're doing this depth, if I'm trying to think of it programming wise, how am I going to have to keep track of things? So the last thing we put in was D. We backtracked to C. C doesn't go anywhere else. Before C, we were at G, and G goes to B. We're okay with that. And before that, it was H, I, F, back to B to A. So now from A, I go to D. I've already checked that. I go to H. I've already been there. I backtrack up. A goes to E. And I believe I hit them all. Okay. That was depth first with backtracking. All right. Breadth. Go wide. One is deep, one is wide. A goes to B. It goes to D.
Does this thing need where to start?
Yeah, we're picking A again. So A has 3 choices, and I'm going to note it again like I did up above. I'm done with A. So now I move to B. B goes to F.
Goes to I.
B goes to F. That's it. I only want to know where does B go, and I'm done with B. Now I go to D. D goes to H, so I'm done with that. I go to E. E goes to H. I already have that, so it doesn't go. So again, I'm going to have to do that whole check of I already have that. Now I go to F. Where does F go? To I. Where does H go? Nowhere.
Did you forget the C that
Probably.
D goes to? Yeah.
Probably. So let me backtrack. A goes to B, D, and E. So this was my first group. I like how I'm doing this. From A, it's one path to B, D, and E, right? So now anywhere these guys go would be a 2 group from it. So B goes to, we said F, and is that it, correct? D goes to H and C. That's the one we missed. E goes to H, we already have. So really this group right here, and I'm still not done. This group right here would be 2 flights away kind of deal. Okay? Because I had to go from here to one of these to get to one of these. Sorry about my C. All right. F goes to, what do we have?
I.
I and
G, which is unused.
Good. H goes to nobody.
Nowhere.
And C goes to
used.
It goes to B and D. Okay. Coming out of there. Need to check this, which actually I'd have to go from A to one of these, to one of these, to one of these. So really, I'm looking at if I wanted to get to I from A, I know it's going to take 1, 2, 3 flights. Okay. 1, 2.
This is actually very nice.
1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like I'm done. So I could even stop here if I wanted to. But if I check, I goes to H, it's already used. G goes to B and C, they're already used, and I'm done. And again, this is 1 flight, 2 flights, 3 flights. So what we're going to do on Tuesday is we're going to do Traveling Salesman. If he wants to start at A and get to I, by looking at a breadth search, he knows he needs to go 1, 2, 3 flights. If he wanted to get to F, 1, 2. Then it would be a matter of finding those 2 to find out which the shortest one is. But we're going to talk about something called the Traveling Salesman on Tuesday. Should we do one more? Or do you got it?
Got it.
Everybody says they got it? Okay. That's cool with me. So I'm going to stop the video and